Hello everyone, this is Rahul Kumar working jointly with Dr. Sheikh Farooq Ali and Professor Shayan Gupta. Today I am going to talk about the analysis of bladed disk systems where system parameters are having random spatial inhomogeneities. This is the outline of the presentation where I will start with the introduction followed by literature survey. Then I will talk about the gaps identified and the objective of this study. Subsequently, I will talk about the work carried out to meet the objectives and then summarize the salient outcomes from the work. Well, spatial fluctuation in geometries or material parameters are inevitable in engineering structures even under the stringent quality control. The possible reasons are manufacturing tolerances, wear and tear, and many more. These fluctuations are typically small and can be neglected if one is interested in characterizing the mean behavior of the system. However, for target reliability based design, these inhomogeneities need to be considered in the analysis. In the present study, an example of bladed disk system has been considered, which was essentially given as a project by GTRE. If we look at this aircraft, one of the important component is this rotating gas turbine, which consists of a series of bladed disk system, which we can further thought of as an assembly of a repetitive unit called sector. At design stage, these sectors are identical and called as a tuned system, whose typical response will look like this, where all the blades have identical response. However, GTRE informed that these blades are manufactured by 3 different vendors, and due to manufacturing tolerances, none of the blades are identical and hence leads to the case of random mistuning, which has been considered in this present study, which is different from the traditional mistuning, which is primarily due to the localized defects in one or more blades. A typical response of a randomly mistuned system is shown here. It can be seen that the response is very different from their tuned counterpart, and few of the blades have amplified response, which affects the operational efficiency, and therefore it highlights the fact that these uncertainties need to be accommodated into the mathematical framework, and this implies the need to adopt the probabilistic approach in the analysis. For modeling these uncertainties associated with system parameters, there are a couple of methods. One is random variable approach. When correlation length scale is more than the geometric dimension of the system, one needs to adopt the random variable model, which implicitly assumes the homogenization of system parameters across the spatial extent, as can be seen here in this diagram. And to propagate the uncertainty associated with system parameters, Monte Carlo simulation based approach is used. The other method is random field approach. When correlation length scales are more than the less than or equal to the geometric dimension of the system, random field model is used. Here properties varies across the domain, as can be seen here in this representative diagram. When one adopts random field modeling approach, it needs to be discretized and need to be integrated with the existing FE model using the stochastic finite element method. The popular random field discretization schemes are OLE, KLE, and polynomial chaos expansion, out of which polynomial chaos expansion has shown mathematically to be the optimal and has been adopted in the present study. Now, for modeling the bladed disk system, initially lumped parameter model were used, in which the system is represented in terms of spring and mass. Due to this simplicity, the associated computational cost is also low, but it is unable to capture the dynamics of the complicated real bladed disk systems. An alternative of this is the finite element based framework, which is being widely used in the industry. For accurate analysis of the complicated industrial bladed disk system, high fidelity FE model is used. This results in large order system matrices in the governing mathematical model, solution of which is computationally challenging. As a result, it is difficult to use in its present form for the probabilistic characterization. The gaps identified in the literature are as follows. In the present, the existing studies model the input uncertainties as random variables. As discussed in the literature, this assumes homogenization of the property over a spatial extent. However, experimental data shows spatial fluctuations as well. Therefore, it is important to model such variabilities as random field. Out of several techniques for random field modeling, PCE has shown to be the optimal, which gives lower stochastic dimension. However, PCE has been mostly used for the regular geometrical domain, but in the present study, bladed disk system has complicated geometry which poses additional computational challenges, and hence a framework is required to address this issue. For a stochastically parametered bladed disk system, along with spatial discretization, random field discretization is also required, and inclusion of this stochastic dimension along with high fidelity FE model further increases the computational challenges. Therefore, a mathematical model is required to address the computational issues. As the fluctuation in system parameters are random in nature and can follow arbitrary distribution, therefore a framework is required to take into account the system parameters following arbitrary distribution. The objective of this study is to model the random spatial fluctuations using probabilistic techniques. To address the computational challenges, a stochastic reduced order model need to be developed for large order systems whose system parameters are having a spatial variabilities. Then studying the effect of random mistuning on the dynamic behavior of the bladed disk system, and finally the developed framework is used for analyzing the real bladed disk system. Since PC has been used in the present study, here I will discuss the underlying principle of PC in brief. Essentially, in PC, the random field is projected onto orthogonal random basis. For example, if theta is the input random field, its PC representation is given as here in this equation 1. Here theta is the deterministic projection which need to be estimated. Psi I is the orthogonal basis functions which follows the orthogonality condition as given here. Here delta Ij is the Kronecker delta. Here the selection of orthogonal polynomials depend on the distribution of input parameters. Now, in this case, the basis functions can also be constructed for the parameters following arbitrary distribution. The equation of motion for system whose parameters have spatial fluctuation can be given as here in this equation 2. Here the M, C and K are stochastic system matrices. Ft is the externally applied force vector. Here the propagation of uncertainties associated with system parameters into the response quantities is also analyzed using the PC framework. The PC representation of nodal response of the system can be written as here in this equation 3. Here this AI is the projections which need to be estimated. Now the modeling of random field using PC based approach requires the evaluation of projections over the spatial extent, which is difficult to evaluate for the system having complex geometry. To address this issue, a bounding domain is adopted which completely engulfs the original complicated domain. Then PC is applied over the bounding domain for estimating the random field for the locations that are common for both the domains. For common location in both the domains, mathematically showed that the moments of random field are identical even for the non-Gaussian field. The associated error bounds have also been derived. For numerical illustration, here a 2D random field is considered. As orthogonal basis functions are identical for both the domains, here the projection functions are plotted for both the cases, and it can be observed here that for common location these projection functions are identical. PC based formulation requires second order characteristics of random field, which is typically obtained through the statistical analysis of large data set, but in practice data is only available at limited locations. Construction of random field with this limited data set using PC based framework introduces epistemic uncertainties. This issue is mitigated by following the steps mentioned here. The location at which data is collected is taken to be the random variables, and each of the observation corresponding to these locations are taken to be the realization of such random variables. Once the data is collected, we need to estimate the marginal PDF of each of these random variables and subsequently the existing correlation among those random variables through the statistical processing of the data. Once the correlation is obtained, we need to simulate the correlated random variable xi for having the same correlation as we have obtained in the previous step. Then we need to find the functional form which maps this xi with each of the component of this theta, which is the collection of random variables. And then we need to estimate each of these random variable in terms of polynomial chaos expansion, and then we need to simulate the random field. Following this approach, random field of Young's modulus is simulated, which is following the log normal distribution, and compared with the target PDF which has been obtained through the data set itself, and we can see a very good match has been observed. Now for characterizing the response quantities, dynamic analysis of system is carried out for non-rotating case first. The FE model of leaded disk system is shown here. These are the material properties used in the analysis. First, to reduce the state space dimension of the system, ACREP based framework is used, which essentially maps the full order system into the reduced subspace by appropriately selecting the active modes and degrees of freedom. It should be noted that ACREP is not a modal truncation. Next, we have compared the FRF of the system obtained through ACREP with the full order model, and for that we have taken just 144 active modes and 144 active degrees of freedom, and we can see a very good match has been observed. To compare the mode shape, MAC value has been plotted. It can be seen that the diagonal values are close to 1. It highlights the fact that modes obtained through the ACREP based framework is matching very well with the full order analysis. Now coming to the rotating case, this is the FE model of the system. These are the material properties used in the simulation. And first we have compared the natural frequency of the system, and we can see a very good match has been observed, and the error is of the order of 10 raised to minus 4 to 10 raised to minus 5. And to compare the mode shapes, again a model assurance criteria has been plotted, and we can see the values are close to 1. And we can see that for full order system, the degrees of freedom are approximately 65,000. However, in reduced order framework, it is just 324, and it approximately saves 90% of the computational cost. Next, in this figure, variation of frequency with respect to nodal diameter for the tuned bladed disk system is shown. Tuned bladed disk system has repetitive natural frequency with orthogonal modes except for the 0th and NV by 2 nodal diameter, where NV is the number of plates. Here the dotted line shows different mode families. It can be observed here that with the increase in nodal diameter, mode families may come close to each other, but they did not intersect. This phenomena is known as mode wearing. However, for stochasticity in bladed disk system breaks this symmetry. This figure shows the variation in frequency with respect to nodal diameter for a randomly mistuned bladed disk system. Here, on account of spatial fluctuations, the repetition in natural frequency is no more, and it essentially splits into distinct modes with very close natural frequency. This figure essentially quantifies the range of frequency for different nodal diameter, which is given by plus minus 3 sigma bound, where sigma is the standard deviation of a scatter. It can also be seen that for tuned case, modes never intersect, but in this case there is an overlap in scatter which leads to mode overlapping. Therefore, designer can compute the probability of such mode crossings, and it gives an additional metric for target reliability based design. Next, in studying the dynamics of rotating system, Campbell diagram is one of the important tools. Here it is corresponding to a tuned bladed disk system. It essentially shows the effect of rotational speed on the natural frequency of the system. It can be seen here that the frequency values are monotonously increasing with the increase in rotational speed on account of centrifugal actions. The intersection of frequency curve with different internodal line gives the critical rotational speed. This figure is showing the Campbell diagram for a stochastically parametered bladed disk system, where range of natural frequency corresponding to each rotational speed about the mean value can be seen. Wherever the internodal line intersects the frequency band are reported as critical speed, which a designer should always avoid. Here the variation in frequency value corresponding to each rotation speed is given by plus minus 3 sigma bounds, where this sigma is again the standard deviation of the scatter. Next, the PDF of natural frequency and the tip displacement is plotted when the elastic modulus is following log normal distribution, and we can see a very good match has been observed. And then we have plotted the same for the case when elastic modulus is following the arbitrary distribution, and in this case also we can see a very good match has been observed. Next, the developed framework is used for analyzing the industrial problem. The high fidelity model of the blade profile is shown here. These are the material properties used in the simulation. First, we have compared the normalized natural frequency of the system, and we can see a very good match has been observed, as the error is of the order of 10 raised to minus 5, 10 raised to minus 6. And to compare the mode shapes, we have plotted the model assurance criteria, and we can see the diagonal values are close to 1. Here in the reduced order framework, we have just 18 degrees of freedom as compared to the full order system, where it is approximately 80,000 degrees of freedom, and we can see a very significant amount of reduction in computational cost has been achieved. We have plotted the response quantities such as PDF of natural frequency and tip displacement when the excitation frequency corresponds to the first natural frequency of the system when system is operating at constant angular speed, and we can see a good match has been observed. The similar thing has been plotted for the case when system is having rotating at constant angular acceleration, and we can see a good match has been observed in this case as well. Now to conclude the talk, in this study a framework has been developed for random field modeling for systems having complex geometries. This framework uses limited measure data set and reduces the epistemic uncertainty into the model. To study the dynamical behavior of large order randomly parametered bladed disk system, a stochastic reduced order model has been developed which significantly reduces the computational cost as compared to the Monte Carlo simulation based approach. These are the list of references. Thank you very much.